Hello, this presentation is part of my study on antenna and today's topic is antenna radiation patterns. So let's begin by understanding what an antenna really does. An antenna acts as a transition device. It connects the circuit world with the space around us. On one side, we deal with voltage, current, and impedance. This is the circuit side. On the other side, the antenna radiates electric and magnetic fields. This is the space side. So we can divide antenna parameters into two categories: circuit domain parameters like input impedance, voltage standing wave ratio, and reflection coefficient, and space domain parameters such as radiation pattern, gain, directivity, and efficiency. So in this lecture, we will mainly focus on the space domain and we'll start with one of its most important concept, radiation pattern. Now let's talk about what a radiation pattern actually is. It's basically a graphical way to represent how the power or field radiated from an antenna is distributed in different directions. In other words, it answers the question like which is my antenna radiating the most energy. You can see a simple example on the right where a dipole antenna radiates power outward in all directions. This distribution is usually described using angular functions like P theta phi for power or for I like this E theta phi for the electric field magnitude. When we describe how an antenna radiates in different directions, we usually use the spherical coordinate system. This system helps us represent the direction of radiation using three variables like r, the distance from the origin to a point in space; theta, the angle from the positive z-axis ranging from 0 degree to 180 degree; and the phi, angle from the x-axis in the xy plane going from 0 degree to 360 degree. So we can also convert these spherical coordinates into regular Cartesian coordinates using the equations shown here. X equals r sine theta cos phi, y equals r sine theta sine phi, and z equals r cos theta. This setup is essential for defining the radiation pattern in space. Now let's understand how to interpret the angles theta and phi in the spherical coordinate system. When theta is 0 degree, we are pointing straight up along the positive z-axis. At theta equals 90 degree, we are in the horizontal plane or xy plane. And when theta equals to 180 degree, it means we are pointing downward along the negative z direction. For the azimuthal angle phi equals 0 degree line lies along the x-axis and phi equals 90 degree lies along the y-axis. So any direction in 3D space can be uniquely described like a theta phi pair. You can imagine a pen like you can imagine a pen rotating at certain angles like in the figure, forming a cone around the z-axis. That's how these angles define direction. So why do we prefer spherical coordinates when analyzing antenna direction radiation? First, it matches the natural way antennas radiate, which is outward in all directions from a point, just like a ripple or a wave. Radiation patterns change based on angles, not distances. So using spherical coordinates helps us represent this angular variation for more naturally. It also makes it easy to define and visualize things like cones and planes of constant radiation. Like for example, the figure here shows a cone where theta is constant. This system is ideal for identifying important features in radiation patterns like the main lobe, side lobes, and nulls. Visualizing a full 3D radiation pattern is often complex and difficult to measure, so instead we use 2D cuts to simplify the analysis. There are two main types: azimuth cut. We fix theta at 90 degree and vary phi. This gives us the radiation pattern in the xy plane. elevation cut, we fix phi and vary theta. This gives patterns in the xz or yz plane. You can see both types of cuts shown here. 2D slices helps us understand how the antenna behaves in key planes, especially where it radiates more or less power. When we talk about radiation patterns, we can look at them in two ways. First is the field pattern, which is a plot of the electric magnitude written as this, E theta phi. Second is the power pattern, which is proportional to the square of the electric field. In measurements, we can capture the field using electric probes measured in volts per meter, or the power using a receiver that reads watts. Most of the time, we normalize the data to make comparison easier. For field, we divide by the maximum value E by E max, and for power, P by P max. To better understand radiation patterns, we often use normalized plots. This helps highlight the shape of the radiation clearly, no matter how strong or weak the actual signal is. We also use the decibel scale, which enhances the visibility of small values like side lobes, back lobes, and nulls that would otherwise be hard to see. Here's how the conversion works. For field measurements, we for field measurements we use this equation, and for power it's this. So this decibel representation helps us clearly visualize the contrast between strong areas like the main lobe and weaker regions like the nulls. Let's look at a classic example, the dipole antenna aligned along the z-axis. This type of antenna has a null along the z-axis, meaning there's no radiation at theta equals 0 degree and theta equals 180 degree. The maximum radiation occurs in the xy plane where theta equals 90 degree. If we take a 2D cut in the xy plane, the radiation looks like a donut shape, omnidirectional. In the xz plane, the patterns forms a figure, the H shape, which is typical for dipoles. In the far-field region, the shape of the radiation pattern stays the same. It doesn't change with distance. Only the amplitude drops as you move farther away, but the directional shape remains constant. To be in the far field, we follow this condition R greater than 2d squared by lambda, where d is the largest dimension of the antenna and lambda is the wavelength. If you are too close to the antenna in what's called the near field or Fresnel region, their pattern is distorted and doesn't truly represent how the antenna radiates into open space. So that's why far field conditions are important to accurate pattern measurements. Let's go over some key terms that describe the shape of an antenna's radiation pattern. The main lobe is the direction where the antenna radiates the most energy. Side lobes are unwanted radiation in directions other than the main beam. They are usually weaker and off axis. The back lobe is the radiation in the exact opposite direction to the main beam. Nulls are directions where radiation drops to a minimum or even zero. Lastly, beam width is the angular width of the main lobe, measured at the point where the power drops by 3 decibel from the peak. It tells us how focused or spread out the radiation is. To wrap up, here are the key points from this topic. Antennas radiate electromagnetic waves in a specific direction, not equally in all. These radiation patterns are best described using spherical coordinates with angles theta and phi. Since full 3D plots are complex, we use 2D cuts like azimuth and elevation slices for practical analysis. Normalization and using the decibel scale make the patterns easier to compare and interpret. Far field measurements give consistent and reliable pattern shapes. And finally, the dipole antenna pattern is a great example to understand these core radiation concepts. Thank you for listening.